Alright, so today we will discuss about field effect transistor. We will target its introduction, its working principle, construction, and some other details about this device. And on parallel, we will also try to compare this device with the ordinary transistor, that is bipolar junction transistor, commonly called as BJT. So these are the contents of today's discussion. In the very beginning, introduction to field effect transistor, then its types, and particularly junction field effect transistor, because this is our topic of interest. And then its working principle, schematic symbol, difference between JFET and BJT, which is obviously quite important, and how it can be worked as an amplifier, and its output characteristics, which can tell us more details about its working, and how we can use it into practical applications. So it is a unipolar device, a semiconductor device basically, and it uses voltage at its input to control its output current. So unlike BJT, where we were using current at the input circuit to control its output collector current. So it's a voltage control device, and because it's a voltage control device, so that means we are controlling electric field at input side. So that is why its name is field effect transistor, because you are actually using field to control its output current. So the biggest difference between BJT and FET or FET device is that BJT is a current controlled device while FET is a voltage controlled device. So we can also say that it is electric field control device. So there are two types of FET. One is junction field effect transistor, which is our focus topic that we will be discussing today, and another one is metal oxide semiconductor field effect transistor. So in our next discussion we will discuss about this device. So this is a chart that shows different types of FET. One is JFET. Again, it has got two types. One is N channel and P channel. Same like BJT when we had PNP and NPN. So another type of FET is MOSFET, which has again two types. One is depletion type and another one is enhancement type. Then each category has got P channel and as well as N channel. So it's quite straightforward that it's also a three-terminal device that either uses electron or holes for the conduction of current. However, in BJT, you remember that we were using holes and electrons both at a time for the conduction of current. And this is the historical information that JFET was also developed at the same time when we were using ordinary transistor, mean BJT. However, it came into limelight of engineers and scientists quite late in 1960s, and in junction field effect transistor, the conduction of current is either by electrons or holes, and it is controlled by the electric field. So that's quite generic statement for FET. So because it is used as reverse bias, means its input is actually reverse bias to operate this device. So its input impedance is quite high, and another thing is it's a low noise device. This is the construction of JFET. On the left side, you can see that we have a N-type bar, and we have two junctions. Both are P-type, and we can see that there are three actually ohmic contacts. Actually, there are four, but these two terminals, they are internally connected, and you just have to apply voltage from outside from a single ohmic contact. So that's why one is drain, another one is source, and the third one is gate. So if this bar is N-type material mat, then we call it as N-channel JFET. And if it is P-type, so we call it as P-channel JFET. So basically there are two types of JFET devices. One is N-channel and another one is P-channel. And in this discussion, we will target only N-channel FET. However, all the working principle, operation, everything remains same for the P-channel JFET. Only you have to change the polarities of batteries. We will discuss it later. And these are some details that if the bar is of N type, it's called N channel. We already discussed, and similarly, it's P channel if the bar is of P type. So there are two PN junction forming diodes you saw that we were calling gate terminal. So only one terminal is taken out for designing the circuits. So because there are two gate terminals but they are internally connected, so that's why from outside you will see only one terminal from the gate, and the other terminals are source and drain. So as far as polarities are concerned, because it's important for the normal or active region operation of this device, it's important to reverse bias. These two terminals are reversed by this junction. So you better know how we can reverse bias any diode. So that's what you need to take care of. And as far as drain to source voltage is concerned, we normally apply positive over here if it is N channel, and here negative if it is P channel. So you see everything is almost same. Just you have to focus on the polarities when you're operating these devices. So this is VGS, get to source voltage. You have to reverse bias for the normal operation. And drain to source terminal, they are interchangeable. So anyone can be used for output or input, but mostly is the common practice is that drain is at higher potential for its common purpose. So these polarities we already discussed, and here it's quite important because the drain gate current, because it's working as reverse bias, so gate current is almost zero. So that's why we can say that source current and drain current, they are equal. Unlike in BJT, we were using this equation that emitter current is equal to base current plus collector current. Or for simplification of the circuits, we used to say that collector current is almost equal to emitter current, and we used to neglect, but still the base current in BJT, it's in microamperes. However, in the case of FET, it's quite small, and this is the working principle, that you can see that there are two depletion layers, one on the left side, another one is on the right side. So if we apply the voltage to reverse bias this junction, so what happens that the width of depletion layer on both sides, because this terminal is internally connected here, so it will start increasing, and due to this the width of the channel will decrease, and as the width of this channel decreases, the drain current will decrease. So we can easily say that normally when there is no voltage here, the width of the channel is quite large, so easily there can be more current can flow from this channel. However, if you increase the voltage, these depletion layers will keep on increasing its thickness, so that will create narrow path for the current to flow, and as a result the current will be decreased. So greater the reverse voltage, that is VGS, so wider will be the depletion layers, and that will cause the main channel for the current to flow would be narrower. So narrow channel means greater resistance, and hence the source to drain current will decrease. So reverse will happen should VGS decrease. That means if you keep on decreasing the gate to source voltage, so the thickness of these depletion layers will start decreasing, and obviously now more current can flow. So this is some detail that if VGS is 0 means here there is no voltage or it's grounded. So now its normal channel width would be there. So as you keep on increasing voltage across drain to source, so the current will increase. So, but if you increase get to source voltage here, so what happens that these depletion layers will start increasing their thickness. So now the channel would be narrower, and that means there will be more resistance, and that will cause current to decrease. So it is clear from the above discussion that current from the source to drain can be controlled by the application of potential or electric field on the gate that we already discussed. And this is the reason that we call this device as field effect transistor. So in terms of P channel, it also operates in the same manner. However, you just have to flip up the batteries, and in P channel, holes would contribute for the conduction of current. Well, this is perfect analogy to understand FET device, because just understand that here water is flowing from source to drain, and there is another terminal. Normally in a tap, a water tap, you have that control to manage the flow of water. So same is the case for here. Just consider this is an FET device. We have gate terminal. You apply the voltage. Higher the voltage in reverse bias, we have less amount of current flowing through drain from source to drain. So if we have zero potential, means this tap is completely open. That means there is complete path for N channel for the current to flow from source to drain. Yes, it's quite helping to understand FET working principle, and these are schematic symbols. If the arrow is inside, I mean if it is going inward, that means it's N channel, and if the arrow is outside, it is P channel. So here we have written, and the vertical lines, they are source and drain. The top one was source, and the bottom one was actually source. So here is a table that shows the comparison of JFET and BJT. So as we already discussed that in JFET we have only one type of charge carrier, either it is electron in the case of N channel, or holes in the channel in the case of P type or P channel. While in BJT both the type of charge carrier, they contribute in the conduction of current. JFET, it's a unipolar device. However, BJT, it's bipolar. And because we apply reverse bias voltage at the input side of JFET, so that's why it has got higher input impedance. While in the case of BJT, normally we operate it in forward bias. That means its input impedance is quite low, and because it's operated in reverse bias condition, that's why the gate current is almost zero or quite small, that we can easily neglect. However, in BJT we have base current in the range of microamperes. Another thing is in JFET it's a voltage controlled device, because at the input you provide voltage, reverse bias voltage, to control output current, while in BJT we use base current to control output collector current or emitter current. And in JFET we normally use transconductance, that is the ratio of output current change to input voltage change. However, in BJT we have current gain normally. And JFET is low noise device. If you remember in the very beginning of the series, with these slides I talked that it doesn't generate much noise. So that's why it is used in different communication systems. So the reason behind that is because the flow of electron is not through any junction. However, in BJT we have junctions. through which the current has to pass. So that's why here we have noise in BJT, but in JFET it's quite small. And JFET can also be used as an amplifier. I think I shouldn't say it can be used. In fact, it is used for an an amplifier as well as a switch because it's a transistor. So here, one example has been given that we have a reverse bias voltage battery connected from gate to source terminal, and output is received from the drain to source using a capacitor that would only allow AC signal. And here we have signal. So let's just assume that we have a negative pulse at the input signal. So what would happen that the overall the voltage would increase and the output would decrease. However, once we have a positive pulse, so what would happen that the overall voltage at gate to source terminals, it would be decreased, and that decrease in the voltage will cause increase in the signal at the output side. So, the understanding is that even a small or minute change at the input side will cause huge change at output. So we can say that if we have a weak signal, so that can be easily amplified to receive uh, high powered signal. So here, the same point that I discussed, that a small change in the reverse bias on the gate produces a large change in drain current. This fact makes JFET capable of raising the strength of a weak signal. So yes, if you provide a weak signal, so it can easily increase the strength or power of that signal. So here the process is written that how we can, how this device increases the strength that I already discussed. And so these large variations in the drain current can be, converted into voltage using a load resistor. So this is quite interesting topic and output characteristics because this device is voltage controlled and output is normally in current. So drain current is there. So just a quick example. So for example, we have a fixed VGS, means at gate to source voltage, we have kept it constant. Let's suppose 1 volt. So as you increase drain to source voltage, because your channel works as a kind of a resistor, you can say. So if you apply voltage here, so the current will increase, and that would be proportional to the voltage that you apply. So that you can see in this graph that current is increasing at fixed VGS. However, if you connect VGS to a higher potential, means in reverse bias we are saying, so obviously that current will keep on decreasing because the depletion layer thickness would increase, and that will cause a narrower channel width. So that's what it is, the details are. So here there are some important points that should be noted, that it's a 3-terminal voltage control device, and JFET is always operated with gate to source with this junction reverse bias, and that's the reason that its input impedance is quite high and the current gate current is 0, and that's theoretically. Practically it's little bit which can be ignored, and due to no current flowing into the gate terminal, so we can easily say the drain current and source current, they are both equal, and in JFET must be operated between these two ranges. One is when there is no voltage at VGS terminal, and another is the VGS cutoff voltage. So that's the maximum voltage that you can operate. And if you follow this range, what would happen if there is VGS equals to 0? That means there will be maximum current, and that is called IDSS. So the drain current when gate terminal is shorted, and to the minimum current, that is 0, and that is only possible when you have VGS equals to cutoff voltage. So there are two gates actually which are associated with JFET. However, you see when you use this device in practical way, you just find only one gate. That is only because these two gates are internally connected. And another feature of these devices is that there is no thermal runaway, because you know that the current doesn't pass through the junctions, and the drain current is controlled by changing the channel width actually. So, and you know that channel width is controlled using VGS, and JFET has no current, and that is the reason that we don't have any involvement of beta like in the case of BJT. And we can just find out how much current is flowing using second order equation. And in next lecture we will discuss about that how we can find out that current and some other mathematical understandings about this device. So thank you so much.